Hi, my name is Chris, N9CVR. In this video, we're going to look at measurements as they pertain to ham radio. Now, one quick note. I know I had said in the last video that we'd be doing basically looking at the performance of that Yagi antenna, and it turns out kind of life happened, and I'll get that next week, I promise. But let's look at measurements here. First thing, let's talk about types of power, in particular types of electrical power. So everybody's pretty familiar with batteries for, let's say, hey, why not a radio? Basically, you got your battery. Sorry about my 4-year-old drawing here. And this is usually the minus side, and this is usually the plus side. And then you're going to send it to, let's say, a switch or something like that. And then you'll have, let's say, a light bulb, something like that. And here we go. If I close the switch, the light bulb turns on, and there's your circuit. Now, what's actually going on there, and let me grab a different color here. Try that on for size. Nah, doesn't work. Okay. What's going on here a little more specifically is I have electrons I've got electrons that want to flow through this wire, because it turns out that wire is a good flower of electricity. And so these electrons are kind of going to sit here like this, and they're going to want to go this direction. The problem is, okay, they will for a few short fractions of a second, and then they're basically going to sit right here and realize that, hey, I can't jump the gap, and we'll have a very quick backup of electrons just sitting here waiting to get through. And therefore, nothing's going to move. Once I close the switch, now current will be able to flow. These electrons are going to continue around the circuit through the light bulb, and that's what's going to cause it to light up. Basically, the electrons going through the light bulb are going to generate heat. The heat comes with light. The light is what we're interested in. And really, the whole thing that's driving this is I have too many electrons over here, not enough electrons over here, and the whole thing just kind of wants to balance itself back out, and we can use that to our advantage to light up the light. This is called direct current, because the electrons only will ever go one direction, from minus to plus. This is, by the way, for the electronics nerds, called Electron Flow. There is another way of looking at it that is sometimes a little easier to analyze circuits, but it's not technically correct, where I have positive charges here that want to go this direction. But again, what would that look like? What that looks like is in any one of the atoms in this wire, there are protons, neutrons, and electrons. That's what make up the metal of the wire. And this, what we call conventional flow, is kind of predicated on the idea that the protons flow from plus to minus. Well, protons can't move. So that's something that historically we thought was accurate is not. It's sometimes still helpful to think of it that way when you're analyzing a circuit, but always remember, in reality, the electrons are what are going from minus to plus. And they're going in a constant stream. Now, contrast that to And I'm debating, I'm not even going to try to draw it. I'll draw it like this. Contrast that to, here's my electrical plug, and I have two wires coming through here, and over here I have a switch, and it goes through a light bulb like this. Now, hopefully you kind of recognize that as something that might get plugged into a 120 volt outlet. Outside of the United States, it might be 240 volts, but the same thing applies. And basically what happens here is same thing. I have electrons sitting here that want to go this way. However, after a certain amount of time, it's actually going to switch, and now I'm going to have electrons sitting up here that want to go this way. So you constantly have this back and forth. I have current flowing this way, and then I have current flowing this way, and then this way, and then this way. And my drawing abilities are deteriorating really, really quickly. Well, this is called alternating current, because, as the name suggests, you have the electrons that want to go one way, and then it'll reverse and go the other way. And if you do things right, for example, with Christmas lights is a great example, cheap Christmas lights, you'll actually almost be able to see that switch in direction, especially if you do something like take your fingers in the shape of, like, if you're showing somebody the number 4 and kind of wobble them around in front of the lights, you'll start seeing that, wait a second, that the lights are almost flickering, and it also kind of looks like I have more than 4 fingers. And what's going on is that's a byproduct of that current going back and forth. And it also has to do with the fact that most Christmas lights these days are LEDs, not actual lamps. But that's kind of away from what we're discussing. So let's see. How can I do this? I'm going to go grab a new image here real quick. So when you look at a plug, terrible drawing of a plug, but whatever. We just talked about how current is going to want to come out here, and then a short amount of time later, I'll say, time plus some number, I don't know what, it's going to want to come out here. This is what's called frequency. And you may have heard pretty commonly in the United States, this would be 120 volts, 60 hertz. And excuse my absolute inability to draw here. What this 60 hertz means, and this is bringing up another measurement unit. So we just talked about volts, which is, we talked about a couple of things that we'll get into in just a second. But let's look at the frequency. What hertz is, it basically means the correct unit for hertz is 1 divided by seconds. Yeah, sure, let's do SEC. There we go. So when you say 60 hertz, that means something happens 60 times per second. Well, it turns out what happens is if you took a graph of this, so here is 0 volts and this is time here. That looks like an X, I'm sorry. Here's the voltage. You'd basically see something that looks like this. And we look at, okay, right here at time equals just a hair above 0 because I don't know how to draw. The voltage starts climbing this way. Well, when's the next time it starts climbing this way? Hey, look, it's over here. It climbs this way. So this right here is called one cycle. And notice it goes positive and then it goes negative. So this is basically where those electrons reverse. And this cycle happens 60 times every second. Well, it turns out that using a little bit of math, we can turn that into what's called a wavelength. Essentially, if I have a wire here sitting over here, let's draw two wires that don't touch almost, and they go to the same electrical plug over here. Horrible drawing, I'm sorry. You can see how long of a wire you would need to get to a point, let's say right here, where you actually see 0 volts. And that would be the wavelength. And basically what you do is you say, if I have a frequency, F, and this really depends on how fast this wave is moving. And in terms of electricity, we can usually make a good approximation by saying, hey, these electrons are flowing at the speed of light. So you have frequency, and that is going to equal 300 million, but I'm just going to put 300 for a second, divided by the wavelength, and they like to use this Greek letter lambda. Now the catch here, the wavelength is going to be in meters. The frequency is going to be in millions of cycles a second. So millions of hertz. And we're going to jump into that in just a second, how that looks. And 300 turns out that actually 300 million meters per second is the speed of light, give or take. So basically you can calculate now, if I have 60 hertz here times 300, or equals 300 million divided by the wavelength. So you can figure out what the wavelength of a 60 hertz electrical connection is. And I did it once, and it turns out to be millions of meters. It's a really long number. So essentially, if you wanted to, where this comes in is you have this interplay in radio where I have this electrical wave, and if I put it through the right length of wire, that wire will, in a way, kind of resonate and give off radio waves. So what length wire? Well, if I want to make a 60 hertz transmitter, I will need millions of kilometers of wire, probably tens of thousands of kilometers of wire. So that's not really practical. However, when we start talking about millions of hertz, suddenly we start talking about tens of meters or single meters of wire. And that becomes a lot more practical to build an antenna out of. So that's frequency and wavelength. So we've talked about different types of current, direct current and alternating current. And we've just talked about frequency and wavelength. Really quick, let me say this. If I have a direct current, so instead of this red sine wave here, if my voltage looks like this along this wire, what is the frequency? Well, nothing ever happens per second, so there isn't really a frequency. So there isn't really a wavelength. So when you talk about direct current, you kind of can't do a lot of the stuff that makes radio work. So radio is pretty specifically an alternating current phenomenon. And those currents have to alternate at certain frequencies that are going to be a lot higher than what we see coming out of the wall. Otherwise, it's just not going to be practical. So, let us, new image, and let's talk about this really quick. I just threw this out. Let's say we have this wall plug sitting here with bent prongs, and it comes out to a switch and a light bulb and back to the electrical plug. Well, we just talked about how, at least in the United States, this is 120 volts. Now, we're going to end up in a future video talking about a certain thing called a resistance that basically, think of it as this is an obstruction of some kind. It's a light bulb, and it's an obstruction to all of these electrons that are sitting here wanting to move this way. And depending on the size of this obstruction, more or less electrons are going to go through per time. Well, that is called a current, and it's usually labeled I. And that is measured in amps. There we go, amps. And it is literally just a measure of how many electrons per second want to go through this little racetrack. Another way of thinking of it, using the term current, maybe makes you think of, for example, rivers and something like that. Home plumbing systems. The current or flow rate would be in gallons per minute. So amps is basically just the electrical equivalent of gallons per minute coming through your plumbing. Now, this, and there can be a lot of argument back and forth. Does current and a restriction cause voltage, or do you have voltage and a restriction and that limits current? And I don't really want to get into that, but going backwards a little bit, basically what this voltage is in our analogy, if amperage is the flow rate, the voltage is basically the pressure. And in fact, we usually call it voltage, but the correct term for this quantity is electromotive force. And it literally is a force that pushes, if you will, these electrons along this wire back to the positive side of the battery. Or in this case, pushes them this direction for half a cycle to the currently positive side of our wall plug. Now, again, voltage is like a pressure. So the harder you push, if you want to say, the more you can do, the more energy there is to use. However, the amperage is kind of, in a way, what's actually doing the work. Yeah, we'll get into this a little more in future videos, but that's kind of all I want to say with this for now. However, there's a really interesting thing that happens, which is here I have something pushing hard, and here I have, or pushing a bunch of electrons hard, and here I have a whole bunch of electrons moving through here. And if I do my math right, and it turns out if I say voltage, which for whatever reason in electrical E's is E, sometimes it's also V, times the current, I end up with the amount of power that this circuit uses. And power is in units of watts. Watt? No, sorry, bad joke. You may slightly be familiar with watts. For example, you can buy, let's say, an 800 watt power supply for a computer, or back when incandescent bulbs were a thing, you'd have a 100-watt light bulb. That basically says how much power is being used by this light bulb. And it turns out to be just the amount of volts times the amount of amps. Now, it turns out that power as we feel it, I'll say, in terms of, for example, audio files, it's as we hear it. In terms of power here, it can be how much power radiates off of an antenna or something like that. Yes, it's additive, because if I double the voltage, I double the power. However, how far it gets out is more a logarithmic thing. So if you've seen a logarithmic formula, it kind of looks like this in a way. This is a bad drawing. But basically, you give me 0, I'll give you 1. You give me 1, I'll give you 2. You give me 2, I'll give you some other number. And it kind of increases like this. So what becomes a lot easier to deal with is, okay, well, every time this power becomes a factor of 10 bigger than itself, so let's say over here it was 1 and over here it's 10, and then if you continue this somewhere it becomes 100. Let's just look at these numbers, and we'll call this 1. Whoops. Don't know what I was drawing there. We'll do this again. 2. Oh, my screen appears to have died for a second here. So this would be a 1, this would be a 2, this would be a 3, etc. 1,000 would be 4. You'd have something like this. Well, that is the decibel scale. There we go. Now it works. So you have this power in watts, or you can have power in decibels, and you can kind of convert between the two. All right. Before I get into more stuff, which I think will be another video, I want to bring this in really quick. Very quickly you run into an issue, because let's use the example of watts. If I have a radio transmitter that puts out 100 watts, okay, that's easy to understand. When you start looking at something that puts out 1,000 watts or more, it becomes a little harder to basically keep track of all the zeros. When you get into these circuits like this, so here I just have a simple light bulb, but maybe there's a resistor somewhere in here. That was supposed to be a resistor, sorry. There might be a capacitor in here. Well, some of these components will have either really, really large values or really small values, depending on what they do. Capacitors, for example, hold charge. So they basically accumulate electrons on one plate. And it turns out, they're really not going to accumulate a ton of them. So the value of a capacitor turns out to be a really small number. So we use these numbers here, and you might be familiar with some of these. For example, here, 1,000th of, let's say, a meter is a millimeter. and it uses the little symbol M. So for example, if you're looking at meters, you might look at mm, M for meters, and then M prefix for milli. Same thing if you get into microscopes and things like that. You might be looking at, and this is a little different, you might be looking at something on Micron scale or nano scale. These are, again, 1/1,000,000th of a meter or 1/1000,000th of a meter. More familiar is maybe if you start looking at computer stuff. If over here I have 1 bit or 1 byte, let's say, well, 1,000 bytes would be a kilobyte. 1,000,000 of them would be a megabyte. 1,000,000,000 would be a gigabyte, and 1,000,000,000,000 of them would be a terabyte. These days you are pretty familiar with these terms because terabyte hard drives are becoming a, frankly, pretty cheap thing. So that's how these numbers work. And I'll just throw this out really quick when talking about bytes. It's not quite 1,000, it's 1,024, and there's reasoning behind that. Again, that's something that's kind of outside the scope of this video. I don't want to talk about it too much. But when you look at, let's say, voltage, you can have kilovolts, especially when you deal with power distribution systems, how to get power to entire neighborhoods or things like that. Very common, so I just talked about this capacitor here. Capacitance is measured in farads, which is a huge number. So more commonly, you will be dealing with microfarad capacitors, which is sometimes, you usually use this Omicron symbol here, but sometimes it gets just UF, sometimes how it's written. You may deal with nanofarads, which is 1/1000,000th of a farad, and you very well might deal with picofarad capacitors. So these are very common numbers, and it is also very important to be able to switch between these. One thing that you will run into a lot when you're dealing with ham radio is frequencies may be given to you in, for example, 1,400 kilohertz. And you just you have to be able to do the math quick and realize that that's 1.4 megahertz. And that's something that, depending on your radio dial, might be something that you have to do on a pretty regular basis. Again, occasionally you'll get into the gigahertz range, especially if you're dealing with, for example, the 2.4 gigahertz frequencies. It's kind of shared with like Wi-Fi and things like that. Terahertz, we don't deal with that. That's getting into some really high frequency stuff that it's an entirely different ball of wax, is what I'll say. So these are all things that play into when you go to take your technician test. These are all questions that are going to be on there. In the next video, what we're going to do is look at a couple other things. So we're going to look at capacitance and inductance a little more. And then we're also going to look at resistance. And it turns out resistance, capacitance, and inductance do some kind of interesting things when you put alternating current to them. So we'll look at that, and then we'll also look at the actual exam questions. So if you got any questions, please feel free to sound off in the comments. Any comments, again, that's what the comments are for. If you found this video helpful, hit the like button, hit subscribe if you want to see more stuff, and we'll see you on the next video. 73.